the colloquium physics. Today we have Fabio has graduated in physics from the University of Padua, and then he moved to the UK for his PhD in quantum information and computation, right? Then
a long time ago, yes.
Then he moved to the US first at MIT as a research assistant, and then in Houston as an assistant professor. And I guess in Houston you start working on developing methods for machine learning for the virtual puppets.
Applied to neuroscience, yes. Even at MIT before, yes.
And today Fabio is at the University of Trieste as a senior researcher. And he's going to talk to me about the importance of choosing the right finance in your machine learning models. And Fabio, the floor is yours.
Thank you for the invitation. It's a pleasure to be here at MIT. So I would like to start with the subtitle, which is why you should carefully choose your model instead of adding a layer. So this is a sort of joke that we have in machine learning. I mean, probably you have already seen these pictures. So we have a guy with a strong statistician that is saying, gentlemen, our learner over-parameterizes and over-generalizes because of the monastic nature of your kernel and blah, blah, blah. And so you see that the performance is going bad. And then you have this guy with this space here, this is another layer to your neural networks we see is working. Here is another joke of the same type. This is your machine learning system. You pour the data into this bag of file, this big pile of linear algebra, and then collect the answer to the others. What if the answers are wrong? Well, just clear the file, and then you see that everything will go in the right way. Actually, this is sort of true, and there was a big debate at some New Rips conference some years ago about theoretical approach versus more practical approach here. And actually, adding a layer sometimes helps, but only in certain domains, like images. Okay. The main message of this talk is you should carefully choose your model, the priors to your model, to match the data statistics and the data geometry in order to do a serial job. So let me take a long route, let's say, in order to go to the point. And start say a few words about what guides humans in discovering laws of magic. This is, of course, a big question. I'm just giving a small definition here. I say that a physical law is as powerful as it describes the deepest amount of experimental evidence. This is what the physicist will tell you if you ask him or her about this question. But if you see it in terms of machine learning, if you want informatics, computer science, a physical law is just a very efficient algorithm to describe nature. Okay. So the key points, or at least the points that I thought about, that are important in order to formulate physical laws, are the ability of select important variables to describe your phenomena. There are things which doesn't matter and things really matter. And then when you have those variables, you will be able to try to find the simplest function that of those variables that explains the experiment. Okay, this is, let's say, my definition of physical. What are the advantages and the problems related to this approach? Well, the advantages is that you have full control and understanding of all the steps you are doing. You do the math, you have learned the math, and you have full control of what you're selecting and the law you are doing. The big advantage is that this process is limited to your understanding of the problem. And if you want to be philosophical, to your sense of beauty is formulated by physical law. Okay? Now let's go to what, let's say, an artificial neural network. How does an artificial neural network solve the problem? I will specify later in the next slides what I mean by artificial neural networks, but the problem can be formulated very roughly as follows. You have a bunch of inputs, you have a bunch of outputs, so you want to find a function that interpolates somehow the inputs and gives you the output. So you want a predictor. So now think about something complicated that is a function approximator, and I will tell you more in a few slides. I was saying, and call this neural network. Okay? The neural network naturally works with the very raw data. Means you don't have to select variables. If you think about trajectories, just give me the images, okay? Just give me the raw data. And what are the advantages of this approach? Well, there is no bias. You don't put any bias there. As you will see, there are a lot of biases in formulating machine learning models. But this is after the talk, okay? But at this level, there are no biases. The data speaks for themselves. So this is a good advantage. Disadvantage is that the result oftentimes are difficult or even impossible to interpret. So let's start to do a very simple and short story of neural networks and start from the simplest one, which is a classifier, okay? So suppose you have in 2D a bunch of points, so they are vectors of 2 dimensions. And to those vectors, you attach a label, which is a +1 and -1. Yes, +1 is -1. To learn how to classify these points, these clouds of points, means to be able to learn a separator, which is this dotted, this line here, that is able to say, given an xi, is it plus or is it minus? One very simple form of it is a linear separator, which is of this form as a line, okay? And then you attach a nonlinearity, which is the sign, to say the prediction is +1 or -1. This has been, done in this early form in 1943. It's called the perceptron, and was inspired by how neurons work. Okay? So what does a neuron very approximately does? It takes an input x and then multiply. So it's the dot product with the weights, neuronal weights, and then spits out an output and filter through a nonlinear function that can be a sigmoid with some threshold. Okay. Which is, if you want, very similar to what you're having here, but just the sign, just change the sign with the signal. We can think to go slightly more complicated in this scenario and say, okay, let's add more neurons. Okay? So each neuron has its own weights, and then you collect the weights into the columns of a matrix, and then you can, make this predictor here slightly more complicated. And instead of having a neuron, you have many neurons, and you have a nonlinearity that is acting pointwise on the output of this matrix vector multiplication. Okay? And then at the top of it, you have another bunch of weights that gives you the output, if the output, for example, is 1. So already with this very simple, let's say, parameterization of a function, you obtain universal approximators. There is a theorem, Cibenko, I think, of a few years ago, that is saying, add enough neurons, you can approximate any function that you can give to me, with some degrees of, not super pathological, let's put it like that. So what is the catch? The catch is, of course, in general, we don't have any indication given a function how many neurons you need. Okay, and this may be a problem in general if you have to do computation. So here I just give a very simple example of what a 1D neural network, or better, what is an interpolation for a 1D function using the formalism I show you a second ago. So in blue, maybe you don't see, but there is a true function, and then you just interpolate interval by interval with lines. Okay, and how do you do it? You use this ReLU function, which is a nonlinearity, which is just this function here is the max between 0 and x. In this case, you just need to cut in the correct intervals your let's say, approximators. And then you learn this slope and intercept for each part of this approximation. And then you sum them, and you also learn the way in which you linearly combine these elements. Right? So The form of it is this, and this can be thought as a very simple neural network. Okay, so this is just a 2D example, just to see how things work. So the input function, the x and y, is partitioned. The domain is partitioned into these different zones, and then the relative constant is learned. Okay, so this is how for a 2D, very simple 2D example, you interpolate through this type of nonlinearities and neural networks. Okay? By the way, stop me if there is any question or anything curiosity. So far, I think it's kind of simple. So one can say, okay, why to stop here? Why to stop one layer? Okay, I can add more layers here. And this is, if you want, the general way in which you construct so-called deep neural networks. So you have your text, and then you apply a linear function. Then you apply a pointwise nonlinearity, ReLU, for example. This is the most fashionable one nowadays, and we still don't know why it works as good as it is. It's working. And then you keep on, composing this function. At the end, you have just, if your function is one-dimensional, you just linearly combine all of these guys. Okay? This is called a deep neural network. And the intuition here, I just don't want to go into details, but the intuition here is that you learn to segment regions over regions, okay? And why this is something that makes sense? Well, there are many intuitions, but if you think about for images, for example, images are composed by parts, and parts are composed by parts. If you put together parts, you have wholes. So there is a compositional structure, okay, which is somehow mirrored in this type of architecture. This is, the very general and not specific understanding of how a neural network is working. Okay? In this type of networks, locality has a great role, compositionality has a great role, and so on and so forth. But this is very specific, say, for images. So during learning, what happens, and when I specify what learning means, this kind of partition of space changes to fit, let's say, an error function, which is measuring how good you are doing, okay? So the question is learning of what, and how can I learn this? Well, the important ingredient here is to define what is called a loss function, right? So this is your approximator, which is already described as a universal approximator. This is your output. By the way, here the mistake should be an I. And so you are given this data, xi and yi, you build up this functional approximator to minimize what? The error that you are making between the prediction and the true label, or the true, let's say, value of your function. Okay, so you want to minimize this, and you proceed in the most simple way through gradient descent. Okay, so you learn these guys here and these guys, just apply gradient descent and try to minimize this function. This type of procedure, by the way, is called backpropagation neural networks. Okay? So what's the problem, or not the problem, what's the catch related to this? So this function, in general, this loss function, are highly non-convex. So that there are many local minima that can serve as solutions. So how do we characterize those solutions? And how can we pick one solution among all the solutions? Because there can be, for example, if there is a valley of, same value solutions, how do we pick one? They have all the same, the value of the error. Okay? So one way of thinking about it is to pose the following question. In all these, let's say, information ranking, what is a single neuron doing? If we are interested in this thing, this is linked to the problem so-called interpretability. Okay, so we would like to match our understanding how we process information with what the neural network is doing. Maybe at least I would like to do it because I would like to understand what's going on. Okay. So one way of doing it is to pick up a neuron and say, I maximize your output, and I want to do it choosing the right input. So you do gradients on the input to maximize the output of a single neuron. Okay, this is a very simple procedure. And what you obtain in the case of image classification are things like this. So let me go back a second here. Oh, very long. Okay, these columns of the vector of the matrix here are, let's say, something which is d by d, for example. So you can reshape it into the form of an image. Same thing for x here. Right? And that's what you obtain. So at the first layers, each image here is what a neuron in the first layer like most. Okay. The second layer and so on and so forth for an architecture. So as you see, first layer picks up something which is like edge-like, so they like edges. Second, more like textures, then patterns, and then parts of the image, and then all objects, but combined in a very strange way that is not natural for us. This is not how we learn what the face is. If I have to say, how do you recognize a face? You see eyes, you see nose, you see mouth, okay, and then you say it's a face. Then you compose them in a whole image. Okay. So the problem that we are facing here is the so-called problem of interpretability that have a lot of impacts even in the society. If you think, the use of these guys for image, let's say medical purposes, you would like to know why the neural network is telling you that you have a problem before going to a surgical procedure. Okay, so this is a main problem related to society also, and use of these guys. So the problem here is that what we have seen through the years is that the more we over-parameterize our functions, the more we have parameters and add parameters to learn in order to fit better our data, and so on and so forth, the more we gain in accuracy, but the more the interpretability of the information processing is not good. Okay. So the images that you have seen before, they don't really make a lot of sense, at least to us. But if you think about physics, chemistry, we need interpretable objects. We need operators that are interpretable. We need to compute them and combine them to, for example, generate a physical law that we can understand. This is our bias. Okay. Another point of view is related to different models. So suppose you have a bunch of data, images, but you can think to any signal, something that comes from physics or chemistry, whatever you want. Just pick up, images because that's what you find the most in the internet, actually. So suppose you have two models that, with respect to your task, they are doing 90% accuracy. So which model do you pick? Okay. One of the main messages of this talk is that we need to know the priors the network is using to compute, or the other way around, we need to impose those priors to our architecture. So what does it mean by that? The priors can be of very different nature. So this is a sort of prior which is naturally embedded in the neural network. By the way, this phenomenon is called implicit bias in literature, and I think it's very interesting. So let me make a simple example. Suppose that your target function is the sum of sinusoids. Okay, so the guy here. Then what do? Well, you just make up your neural network and then you try to fit your target function. What you will see is that during the training, the network not only fits from the beginning the lower frequencies and then goes up to higher frequencies. This is something that you, given this network, you don't know a priori, right? So this is a prior of your network in fitting the data that you must take into account if you want to learn how the network is fitting the data. This is one example. This is another example which I find highly counterintuitive. So this is a sort of implicit bias. So the network has a bias in computing information that you don't know, that depends on the architecture. In this case, the architecture is a convolutional architecture. So you have a specific topology in the links of the weights of your neurons, okay, which is convolutional, just doing convolution, okay. And this is what is called a fully connected. So it's just a matrix, basically. You have two matrices. And let's think more in, say, in group theory. Let's say this would be a matrix which is a cyclic matrix. Okay, is implementing a convolution with respect to the cyclic group. Same here, and this is instead of fully connected. So if you have a target function and then you run your gradient descent, these are networks which are linear. You see that you can actually mathematically demonstrate that these guys, so the fully connected, try to minimize the energy of the multiplication of the weight naturally. And you don't know this before. If you do it instead a convolutional network, very surprising, at least to me, the network tries to minimize the 2 over L norm. L is the number of layers, so if there are 2 layers, let's say the 1 norm, of the Fourier transform of the weights. Okay, so it's sparsifying in Fourier the weights. So this has a strong implication on what is picking up in order to approximate your function. Oh, the L2 norm sampling. Yeah. They call it energy intention. There's no energy here, no physical energy. It's just L2 norm. Okay. By the way, this is one of the very few examples in which you can calculate the so-called implicit regularization or implicit bias for neural networks. If you pick up something which is slightly more complicated, you just forget about calculating these biases, okay? The bias in which the information is processed. There are other forms of biases. For example, suppose you have to classify digits. Okay? These are images of digits, and you have to classify at the end of your network. You have to say is it 0, is it 1, is it 2, is it 3. So maybe the image of the digit is presented to you not in a canonical form, but just rotated. So you should know that a rotated 2 is still a 2. So what is the classical thing that you do in machine learning? One way is that you show to the neural network your digits and then all the rotated versions or a sample of the rotated version of the digits, such that you say, this is a 2, this is a 2, this is a 2, and you repeat to the network this 1,000,000 times in order for the function to be invariant to rotations, okay? For the output function. And what you see, at least for a very simple network, this is misleading. What these guys are just for a neural network composed by one layer, not convolutional, is that the symmetries you put in the data, they are somehow mirrored in the weights of the network. Okay, this is a slightly more complete feature. And here I just did data augmentation for a neural network that is engaged in classifying digits. So I just translate the digits, rotate the digits, scale the digits, or do mirror symmetry of the digits, okay? And give all this data to the network, and the network should attach to a scale, the rotated, translated, or mirror symmetric digit, the same label. So the same is a 2, even if it's mirror symmetric. Is this something I see perplexed space? So if you think about groups, of course, just the group of rotations is defined on 0 to pi, and therefore is a compact group on an interval. What you do, you sample the elements of the orbit, if you want to rephrase in more physical terms. And then you can think about applying some, a concentration inequalities and say this is enough to get an invariant function. You get really what you get using this data augmentation is never a perfect symmetry, okay? You don't get an invariant function. You get an approximation of an invariant function. Sometimes it fails, okay? Even so, suppose you don't have the whole orbit, a bunch of an orbit. So just things which are rotated of minus 30 plus 30. In the network, we learn to get an invariant function approximate in that range. Okay, it's actually like our brain. Difficulties in recognizing faces which are up down. Because our data, if you think in terms of primates, I guess, we rarely see things. So you can make this experiment. This kind. Okay, so this is just saying that the statistics of the data has an influence, and you can think as a bias in terms of the computation that the neural network is doing. Okay? So these are the weights, just to be clear. These are the weights of the neural network. So you have, a vector which is d times d, just to make things simple, and then I reshape it into an image which is d times d, and you get this. Okay? Then, more related to the interpretability of the network, one question that this is something that we publish, we pose the following question. So suppose you have a network that is, classifying a dog, and then the question we pose is the following: which are the frequencies of this image your network absolutely need in order to classify the image? Okay. Why frequencies? Because the Fourier transform is something we can interpret. It's arbitrary, but we can interpret it. So you can actually you can train a network, then freeze the weights, and then do the following: adding a layer, a pre-processing of the images, which does the following: take the image, go in Fourier space, multiply the image by a mask, and then go back to the image, which is filtered by this mask. This is just a filter in Fourier space. Well, which is the catch? The catch is that we want this mask is learnable, and what we want to do is to minimize the number of frequencies that the network needs when it's presented this image to classify the image as it was classifying before the filtering. Okay, is this clear? So you have a network that is doing its job, and then I start taking out frequencies from the image. The classification at a certain point will change. So I take out as many frequencies as possible, not to change the classification. Okay? And this can be formulated mathematically in this way, but it doesn't matter. So these are some details of what we use. This is the network, the data set, but they're just details. The important thing is the following. It's too small. These are the masks that we obtain image per image. So we give an image and we say take out all the frequencies that you can in order to classify the image as it was classified without the filter. So the masks, masks for each image belong to different classes. Okay? So the point here is that these images, these masks are very sparse. So you really need, the network really needs very few frequencies in order to classify the image. The surprise is the following. If you filter the image with those masks, something that is classified as a church is classified as a church, but when it's filtered. So this is what the network thinks as most important frequencies and retain as most important frequencies to classify this image as a church. And there are many examples of this. For us, it's just totally not interpretable. And what's the point of this? The point I want to make is that if you change the model, these frequencies which are picked changes. So these can be thought as a fingerprint of the model bias. And these are changing. And if you change the initialization of the model, they change. Optimizer, they change. Change the data statistics, again, they change. So we need to have somehow control on these things if we want to do something which is interpretable and not just black box, add one layer.
sure I understand. So what you're saying is that if I give to given model the image on the right hand side, it correctly classifies it as a judge. Right? So does this mean that I can come up with a nonsense picture that is similar to this, and the model will still tell me it's a church?
Yeah, absolutely. You can even modify this picture with a perturbation that is super small that you don't really see, and this will be classified as a force. Okay, these are called adversarial examples. And here I'm doing slightly a different thing. I'm just saying I want to know what you use in order to classify in Fourier space. Of course, you can use wavelets, you can use other things, but it's just
only on the structure of the images that use pictures, but also what are the images that use of the other category that is that will be different.
Yes. So this depending on the data statistics, because the network will learn to classify all the images, so we'll adapt all these ways to classify all the images, and then the bias is of course reflecting all the images, not only. Okay, so this was a fundamental problem, which is how can we learn interpretable models? One way of this, this is an introductory talk. This is not very technical. I just want to give you pointers how to let's say make sense of your neural network model. Okay? So one way of proceeding is to have a dictionary of interpretable features. So and this has been done quite a long time ago. So suppose you want to, you have an oscillator here, and from the trajectory, you want to infer the law, okay, the physical law. How do you do it? Well, you can just give the pictures of the videos or the oscillating thing to your neural network and try to spit out something, okay, that is interpolating. But then you have a bunch of weights that have some meaning. You have an interpolator which is difficult to interpret, okay? Or you can say, listen, I know that whatever the function is a linear combination of these operators that are acting on my trajectory. So you have a dictionary for them. And then you can use a sort of machine learning to pick up which operators are most important in order to explain the data. So you do what is called a sparsification. So you sparsify, you make all the coefficients zero as possible. Okay, there's a sort of simplicity rule, a way, let's say, Occam razor, if you want to say it more in philosophical terms. Okay? And then this combination will give you the law. This actually has been already done some years ago. This is a paper in Science, and they have some nice results. This is one way of proceeding. More in general, this is another topic that I wanna.
This would work with experimental data and like genetic data and
Yeah. This is, I don't know if they did it, I just have this example. Yeah. My feeling is that this approach hasn't been so successful. Because in any case, you put a bias. This is your bias, okay? This is, I want to work with these guys because I understand them. And the other way is forget about it. I can get better results, but what is this about? And then I will show you a third way, which is between the two, okay? But I think you can do it. I don't think will be very much successful. I haven't seen many papers. Okay. So another thought that I want to give is why do we need good priors on machine learning models besides it? So everyone knows about, I guess, the course of dimensionality. So if you want to, let's say, sample points of a function to interpolate the function in high-dimensional space, this is very simple in 2 dimensions. But if you go higher, this is very difficult because basically, if you want to sample a space, an hypercube with a specific density, then you need basically, what you can prove is that you need basically to cover the whole hypercube, okay, in order to sample it. This is very counterintuitive, but it's linked to the fact that you work in multi-dimension. And this is a problem that you can see in many aspects of machine learning applications, like social networks, meshes, functional networks, anything that is related to CSV graphs, for example. But which is the catch here? Do we really need to finally sample the whole space? If you think about the images, well, you don't need to, because you don't want to sample noise, okay? You don't care about it. So you have to have priors on the statistics or the geometry of the manifold of the images, and to embed them into neural network. So suppose that as it is, the statistics of the features of an image is translation and scale invariant. I mean, there is, if you think about an image, when you detect an edge here, on average, there is no reason why you shouldn't detect an edge here or here or here, right? So there is a sort of translation invariance in the detection of features for images on average, of course. This is why, for example, at least my intuition, convolution works, because you move your detector with equal probability in the same, in all the places of the image. Okay? So the catch here is we need to understand the geometry of our image, come up with good priors like translation, scaling, values, and then target more meaningful spaces of solution. Okay? So the main message of this talk is exploit the geometry of the data and a priori information to come up with new notions of regularity that you use to choose better functional spaces to target, okay, through your neural network. Let me give you a specific example, which maybe resonates more with physics. So suppose you want to implement an invariant function. This is an example of an invariant function. This is a representation of an abstract element of a group G into, let's say, a vector space. Okay. Invariance means this. Equivariance, or as physicists call it, but I think this has been stolen by machine learners into another field. Now they call it equivariance. So the equivariance means that basically you have a function, a representation of, let's say, your signal, your image, and then you transform it with a group transformation, and then this group transformation just goes out. Okay? This is the classical definition that you see in machine learning papers. So suppose that you have this prior. You want to learn, or you want to develop machine learning models that have already these priors embedded in. Okay? So what you do is the following. You restrict yourself to learn equivariant functions, and then we will see some examples of it, with respect to the group of transformations that you are interested in, the symmetries you are interested in, and then you fit those functions with your data. And then you are restricted to a much smaller space of target functions, hypothesis space, that you can learn faster, that you can learn way better. Maybe if you just consider all the functions, maybe the algorithm is not even converging. You don't learn anything. Okay? So let me make an example with graphs. Graph isomorphism is one example. So if you change in the same way the rows and the columns, if you mute rows and columns in the same way, your graph should contain exactly the same information because it's about topology. Okay. So a good idea is to have a function which is invariant to permutation. Okay. Actually, is a very simple thing to build up a function which is invariant to permutations if you have a function which is equivariant to permutation. Okay? This can be done in a simple way. So one good idea is to, in your neural network, to have layers of neurons that build up a representation which is permutation equivariant. And for that, there is a theorem. Okay? If you want something which is permutation equivariant, then your representation have to have this form. It doesn't matter the details, but it is a theorem. Okay, so you just have stuck up multiple layers. Other layer is good, but this form of layers, okay, if you want that property, of course. then, I mean, here you are more expert than me, of course. Suppose you have a quantum system, and then you have you want to find the ground state. So you want to minimize this function, okay? State of minimal energy. And then you have a parameterization of your wave function through a neural network or something like this, okay? Your machine learning model. You know that your Hamiltonian has some symmetries. So you want to embed those symmetries into the structure of the network to target a better space. So how do you do it? Well, you better construct something which is, suppose that the Hamiltonian is invariant with respect to a group. You better construct a neural network which is invariant with respect to the group transformation. Okay? Do we have a general recipe for doing this? Yes, there are two ways. One is to build up an invariant function. One is the most, let's say, simple, let's call it like that. You do data augmentation. And just say, this is equal to this is equal to this, and you force the network to learn an invariant function. Otherwise, what one can do is to structurally build a function approximator, which is by let's say by construction invariant. And this results here, which is linking the properties of equivariance and invariance to the properties of convolution. It was something quite recent, I think 3-4 years ago. Our main result is to prove that convolutional structure is not sufficient, but also necessary condition for equivariance to the rational compact group. So you have a physical system that has some symmetries, and you want to target the right space in order to do approximation with few computations. How do you do it? You have to build up a neural network which is convolutional with respect to the group of the symmetry. Okay, this might be simple, this might be not simple, and so on and so forth. But this is the result. And then I would like to end with this. So what if the symmetries are not evident and we have to learn them? So suppose your physical system, am I doing okay? Your physical system actually has some symmetries that you don't know, but you know that they are there. So you want to know the symmetries and implement them maybe in a neural network. Okay. So here I'm just giving some hints. This is of course not the solution because there is a huge debate and literature about this. So one way of building up an invariant function is through group average. Okay. So if your function is a function on the group, okay, this you can think as the group element applied to it to X, and then you do an average over the group, and this is by definition something that is invariant with respect to transformations of X with respect to the group G. Okay, this is kind of. So what you need is an orbit here. Okay, you need to have this transformation. Okay, any question? Do you agree? Okay, so if you think through convolution, this is what is actually happening for translation invariance. Okay, so this is a matrix that is implementing convolutions with respect to a cyclic group. So this is a circulant matrix, in other words. Okay, so you see this guy and the circulant versions. And this is a form of convolution. This is what is going on in convolution neural networks. The difference is that the number of non-zero weights in the first column is limited. So you have localized kernels. That's what is called. Okay? But at the end of the day, if you want to translate this in more physical terms, you have an orbit. Okay? So what if you want to implement a convolution with respect to an orbit that you don't know? How do you enforce the group structure? And here I'm just giving a pointer because that's not the solution, but one can go like this. So this is the picture, for example, of cyclic matrix. Okay, the colors are just the values of the pixel, and then it's cyclically shifting. So consider the Gramian of the matrix. You see that due to the dot product structure of each column with each other column, omega I and Fabio I, and the fact that these are orbits with respect to something, I suppose that they are orbits, okay? Each of the column here and each of the rows is one deterministic version of the other. This is due to the fact that the group composition is closed. Okay, I don't know if this is evident or not, but it's just a very simple property of the group. So one way to enforce the fact that you have a group implementing your convolutions in your neural network is to add what is called a regularization term to your loss that is enforcing exactly this structure. This is, of course, working for a subset of groups. If you consider, continuous groups, in here I'm just considering groups which are finite. Okay, but this is one way of going in the direction. It's not an if only if, of course, but this is one way. This is how one can think differently from what people do in physics to enforce physical constraints into machine learning. Adding something which is a new regularization term, or as I call it, new notion of regularity that you enforce in your network and you minimize to give structure to the network. Okay. I just wanna, and then of course what you do is you take the gradient of this and you learn the weights, but this is. So if you want to summarize the few very general pointers that I gave to you in this talk, if you use an artificial neural network or any other model in machine learning, and you just don't want to add a layer, you want to understand what's going on, you have to carefully choose the architecture to match the geometric priors of the data loss function, which is kind of evident, but how to do it, that's the tricky part. And then maybe, if you are interested, of course, to test for interpretability of your results. This can be look for which are the main frequencies that the network is using, or what are the neurons actually picking up as a signal. Okay, and I just want to end with some advertisement here. So if you're interested, we just have the second volume of our research topic. This is in computational neuroscience, but focused on symmetries as a guidance principle in artificial neural networks and brain networks, but also with a lot of application in physics, chemistry, and so on and so forth. And this is, me, a guy from the Baylor College, Tommaso Poggio from the MIT, and Eugenio Fabio from. If you are interested, we are looking to find people that contribute. Okay, and with this I conclude. And if you have any question, existential question, just
Fabio? But first,
no. One question. What happens if the symmetry? I mean, symmetry is a very powerful concept, but very often it's useful when it is not perfect. So even when it is not perfect, tell us about the system. The system is almost spherical. Okay, it's not spherical, but so is it useful?
So if you want to implement the science, you understand better. You want to implement the invariant function, even if the type of symmetries that you implementing the invariant function.
Images are the convolution, the story in the convolution neural network are good because the images are translation invariant.
One way.
Because you translate, and because if you cut the image,
average, not on the single image. The statistics, so that you have to have, for example, in the natural images, the power spectrum goes down as 1 over f, which is scale invariant. Okay, so you want a network that is reflecting this invariance somehow. The single image is not, but on the statistics of it, that's the kind of so it is not. Or for example, these images here. where is it? Okay. This one. So these are the weights that you reshape in terms of the image. And what I've done is you show to the network the image of something and the mirror symmetry, okay? Or you show to the network a mirror symmetric image, and you get the same result. This, to me, sounds like even if the symmetry is not perfect, because the image and the mirror symmetry of the image is not a mirror symmetric image, okay? Then, on average, he's picking up the fact that he has to build up something which is invariant. And actually, for this very simple network, I have a mathematical just for this. Then one layer, you 10 euros. If you go up with more complicated things, there's no way of. But maybe I misunderstood your question. I think you were saying if I have a symmetry which is not already, which is not perfect in the data already, right?
Or a system that doesn't really, I mean, a system that has some friction, something, but is almost energy conserving. Is energy conservation a useful concept when the system is almost conserving? I mean, how much?
Yeah.
If you have an imperfect symmetry, is it useful? Is it useful thing?
I think so, because in any case, the network is learning, but this is more of a how the answer say by experience training networks is picking up whatever is useful for your task. So if your task is, I don't know, in the case of what you mentioned, to learn an imperfect symmetry will be useful, then it will learn it perfectly. Okay. But this is data driven. What I was saying there is if I know there is a symmetry, like the Hamiltonian, and this is the thing that gives you the permutation matrices, then I can implement a neural network that is by hand implementing those symmetries. And this will just chunk off a huge bunch of target space, which is not useful.
So my question was about the equivariance, because you mentioned point the between invariance and equivariance, and it is true that I think of several applications in physics where let's say physicists somehow have found out that if you use equivariant descriptors, everything works better. But up to my knowledge, nobody knows why. So it was not clear, at least say the physicist community, why equivariance is a good idea. So why actually having like a descriptor, let's say, that is not invariant, like with respect to symmetries, which as physicists would think that this is not a good idea, actually gives you this flexibility to improve the exact flexibility of your model such that in the end it can deliver better performance. What I want to ask is there more mathematical statement about why equivariance is better than invariance?
Better than invariance?
Yeah, so let's say you have two models and one is invariant or the features that you describe your model, some of them are invariants with respect to the symmetries of your system, and the other. And there are a number of cases in physics, like I can think of total potentials or Hamiltonians, where people claim, I would say, that the equivariance version outperforms the invariance. So it gives you, by outperform, I mean it's more accurate, say. And I was expecting why.
I think it really depends on the task, right? If you have cleared the task, for example, for images, it is clear that an invariant representation is what we have at the end of the pipeline of the processing of the information, because at least we want to say this is whatever it is, independent of the position. Okay. So, but the way in which we built up this representation can be through an equivariant representation, because invariance is just a special case of equivariance. Okay. So if you think to equivariant functions, they are less invariant functions, they are inside the equivariant functions. Okay, so you go to your target point through, but again, this is a kind of wavy explanation. You go to your target point through, the right path. Okay, this is the kind of, similarly for, I mean, I have examples in the image space. Maybe it is not exactly, but when you recognize a face, the right way to go is not to have invariance to translation of the features, because think about what you really care about is the relative position of your nose, your eye, and your mouth. If you consider something which is invariant to translations, to have a mouth that is there, is not a face. So the way in which the neural networks are built in this is you have a feature structure at the first layer, which is convolutional, and then you build up a little bit of invariance by what is called pooling. So you just say, okay, the bar is here, 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 or here. I don't care where it is. I do a max between these pixels, okay? So I built a local invariance. And then the next layer of your neural network is equivariant with respect to the transformation that is left up to that little invariance. So, for example, when you smile and your face is changing through a diffeomorphic transformation, let's say, then you are invariant, you recognize your eyes or your nose, even if it is a little bit translated, let's put it like this, but not too much. Okay, so this is a right way of preserving the relative parts position, if you want. But this is not physics, it's more, this is the kind of explanation I can give.
I think it's stupid curiosity. If I want to learn a fractal function, do I need
Stupid curiosity?
four layers? So a self-replicating.
You need a network which is scale invariant. I mean, this is the first thing that comes to my mind, okay? Something which is truly scale invariant, meaning, for example, something which is implementing convolutions, I would say, with respect to the scale transformation. So you see objects at different scale, and then you implement an invariance, which is scale, you implement scale invariance, okay, such that if you look to your object at this distance or this distance, you see exactly the same thing, because the statistics of the features is exactly the same. So that's what I would say. You need a layer which is scale invariant, which is an abelian group. You can just implement as you do for translation. The difficult things are when you mix translation scale and rotation, because they don't commute one with the other. So it's very tricky to implement things which are invariant, equivariant with respect to non-abelian groups. Okay.
So we were mentioning that you have a function of x and t, and
Mhm.
they tried to reconstruct the differential equation. So my question is, there is a way to reconstruct the conserved quantities without telling them to.
The concept, yes, there is a paper. Actually, I don't remember all the details. Yeah, there is a way, but I don't remember to impose or get fine.
That's first time a combination of the different.
My mind pops up a paper, but I don't remember the details. I think I can send you the paper because I forgot about the details. But it's not a theorem, right? Not a theorem.
Oh, the Bezier system is you have certain things that you see.
Yeah, for example, one can think, I mean, I'm freely thinking here. One can think, okay, this is my trajectory. For instance, I'm thinking about a thing. This is my trajectory. And I suppose that there is a combination of stuff like this that suppose to a large part that this is the case. So the derivative of the combinations of the elements of the particular element needs to look at it, is constant in time. And I do gradient descent in order to find the combinations using this dictionary to build up the invariant. Something like that. One can try. I mean, I don't. Any question?
No, that's